You clicked because you need to know how to bond carbon fiber reinforced polymer to stainless steel for food-grade automation. You need to know this because standard bonding protocols are failing your production lines. You will learn why thermal mismatch is the silent killer of these joints and what specific surface preparation steps are required to survive high-pressure washdowns. In the world of food processing automation, there is a persistent belief in the perfect bond. Engineers and operators often assume that if they apply a high-strength industrial adhesive and follow the manufacturer's cure schedule, the joint will last indefinitely. This assumption is dangerous. It ignores a fundamental physical reality that exists between carbon fiber and stainless steel. These two materials do not behave the same way when they get hot or cold. When you subject a bonded assembly to the shock of a high-pressure washdown, the rapid temperature changes, and mechanical forces expose a hidden weakness that standard testing often misses. Let us start with the materials themselves. Carbon fiber reinforced polymer is a composite made of carbon fibers embedded in a polymer matrix. It is lightweight, strong, and corrosion-resistant, which is why it is so popular in food-grade environments. Stainless steel, on the other hand, is a metal alloy known for its durability and ability to withstand harsh cleaning chemicals. Both are excellent materials. The problem arises when you try to join them. Every material has a coefficient of thermal expansion, which describes how much it expands or contracts when the temperature changes. Carbon fiber has a very low coefficient of thermal expansion. It is dimensionally stable. Stainless steel has a much higher coefficient. It expands and contracts significantly more than the composite when the temperature shifts. Here is the thing that causes the failure. In a food processing line, the equipment goes from room temperature to near freezing during washdown cycles and then back up during heating or sterilization. This cycle happens multiple times a day. Because the steel wants to move more than the carbon fiber, the bond line experiences immense shear stress. The adhesive holds them together, but the materials are trying to pull apart. Over time, this cyclic loading creates micro cracks within the adhesive layer or at the interface. These cracks start small and invisible. They grow with every washdown cycle until the joint fails catastrophically. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This is where the myth of the perfect bond dies. Many engineers treat the adhesive as the primary load-bearing element, assuming the bond strength is the limiting factor. They focus on tensile strength numbers and shear strength ratings, but the real enemy is not the strength of the glue. The enemy is the mismatch in thermal expansion. Even the strongest adhesive cannot completely eliminate the stress generated by two materials trying to expand at different rates. The adhesive acts as a bridge, but if the bridge is too rigid, it will snap. The system requires a degree of compliance to absorb the differential movement. Now consider the surface preparation protocols. This is where most automation systems fail to account for the reality of the field. In the laboratory, you can create a perfect bond on a clean, controlled sample. You can prepare the surface with abrasive blasting and solvents to ensure maximum adhesion. But in a real food processing plant, the conditions are far more aggressive. High-pressure water jets can penetrate micro voids in the bond line. If the surface preparation was not rigorous enough, or if the adhesive did not fully wet the surface, water will find a path into the interface. The presence of water changes the chemistry of the failure. Water acts as a plasticizer for many polymer matrices and can degrade the adhesive over time. When you combine this chemical attack with the mechanical stress of thermal cycling, the bond line becomes a point of failure. The lack of specialized engineering modules in current automation software compounds this problem. Tools like Sharp RPA allow for code-free automation on .NET environments, which is excellent for logic and workflow management. However, they lack the specific material science modules needed to model thermal mismatch coefficients between carbon fiber and steel. Without this software capability, an automation system cannot inherently predict fatigue failure during high-pressure washdown shocks. The system runs on logic that assumes the hardware is static, but the hardware is dynamic and stressed. This leads to a critical gap in the industry. We have open-source tools that enable rapid deployment of automation logic, but we do not have the integrated engineering frameworks to validate the physical integrity of the hybrid structures those automations rely on. The absence of benchmark data on surface preparation protocols in the available literature complicates the situation. We do not have a definitive set of practitioner perspectives that confirm specific adhesion thresholds for these hybrid joints under extreme thermal shock. Consequently, the argument that thermal mismatch causes failure remains theoretically sound, but is difficult to quantify with the current data pool. To maintain engineering credibility, we must qualify that while the failure mechanism is a known risk, the specific quantitative failure rates are missing from the current research pool. This necessitates a reliance on general composite theory rather than specific case studies that are often corrupted or incomplete. The solution is not to stop using carbon fiber or stainless steel. It is to change how we design the bond. You must account for the thermal mismatch by selecting adhesives with a lower modulus of elasticity. These adhesives are more flexible and can absorb the differential movement without transferring the full stress to the interface. You must also implement a multi-stage surface preparation protocol that goes beyond standard cleaning. This includes controlled abrasive blasting to create a specific surface profile, followed by a plasma treatment to activate the polymer surface for chemical bonding. The final insight is that the bond is not a static connection. It is a dynamic interface that must be designed to accommodate movement. If you design for a static load, you will fail when the washdown cycle begins. The system must be built with the understanding that the materials will move independently. The adhesive is not just a glue, it is a shock absorber. It must be thick enough to allow for strain, but thin enough to maintain rigidity for the structural load. This balance is the key to surviving the shock of high-pressure washdowns. Without this understanding, you are relying on a myth that the bond will hold simply because it was cured correctly. The bond will hold only if you design for the thermal reality of the environment. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.